Welcome to this video where we will look primarily at classification of mathematical models. Now, as I stated in an earlier video, this course will involve a series of approximations. First level is the approximation of the physical world through either thought experiments or concepts such as mass energy momentum balances based on the mechanisms that we have understood or are made known about the process, or through empirical modeling using data that's collected from the physical system, we are going to represent the world using the mathematical model. So when I say the world, it could be any social, technological, chemical, biological, environmental phenomena. And as far as we are concerned here, it is going to be about chemical, environmental, and biochemical processes, right? So we are going to confine ourselves to that world, and through the application of conservation principles and other equations like equation of state and constitutive relationships, plus models we make from the collection and analysis of data, right? That is what we call as empirical modeling. Through these two routes, we will come up with a mathematical model. And then if the mathematical model is complex enough, either because it is large dimensional, that means multiple variables, too many variables rather, and sometimes and oftentimes you will see nonlinearities in your model equations, right? A mathematical model. So you cannot solve it by hand, therefore you adopt a numerical approach. So we mentioned all this in an earlier video. So there is one approximation as we go from here to here, and if this mathematical model is simple, then we would go for the analytical route. If the mathematical model is complex, as we will assume in this course, then we will adopt the numerical approach. So this will be approximation 2. This one is approximation 1. So in going from mathematical model to a numerical model, we will again make certain approximations, because that is the only way to solve the problem, because analytical tools do not extend far beyond linear systems or simple nonlinear systems. So for really nonlinear systems, you have no option but to convert the mathematical model into a numerical model and solve it with a tool like MATLAB. All right. Now, why do we have to tolerate such an approximation? Because that's the only way out, as I was saying. One reason is we do not know much about the physical world. We know some portion of it from our perspective, and based on the observations we have made, based on the principles that we have elucidated by working on similar processes, etc. So our knowledge keeps increasing, but our knowledge is not complete. Therefore, in a bid to just represent the physical world in a form of a mathematical model, we are okay with approximations. The second thing is, when we are trying to approximate the physical system with a mathematical model, we typically are interested in a simplified representation. We are not looking for representing every phenomena that we might know, because that might take too much of an effort, and we do not want the model to be too complex for our purpose. See, the model that we develop is always linked to the purpose, right? So if you're trying to work on a very high stakes system, then we have to spend more effort into understanding it, modeling all the important details, etc. But for certain uses, we do not have to know about everything that's there, so we ignore certain smaller phenomena. For example, when you drive a car, you may not know everything about the mechanism of the internal combustion engine, transmission, fuel properties, all those kinds of things. We just look for certain parameters, right? And we know how to get from point A to point B safely. So as long as we know the operation of the brakes, the accelerator, the gear system, the steering wheel, and you know to turn on and off the lights at different points, in a dark environment or when you're making a turn, etc., etc., right? So if you know a few things, you can, you know, uh, drive a car safely. So you don't have to know too many details and put it in your head, etc. Right? So that's the idea. The model that we developed is always linked to the purpose it is going to serve. and whether the stakes are high or low, right? So a model is always fit to purpose, and therefore sometimes we are happy with approximations. As long as we can get by with our approximations, we are fine with it. Remember, model development will take time. It takes resources in terms of money as well, right? Money, people, time. So it involves all that. So we will invest in modeling only to the extent that we would have the need for it. All right. So we tolerate approximations because of that as well, right? So it is an intended approximation or an intentional approximation. Sometimes the approximation is not intentional because we are just ignorant about things that are happening there. So we might make some crude approximations to reality. And in going from the mathematical model to the numerical model, that approximation is required because there are no analytical solutions possible for the mathematical models that we develop, right? I have touched upon this point many times. So therefore, in this approximation A2 is something that we cannot avoid. So people there also are discussing many methods that will make the approximation of the mathematical model more and more accurate, right? So you get more and more accurate. That means the gap between the numerical model and the mathematical model can be reduced by interesting numerical algorithms, etc. Right? The way of converting a mathematical model to a numerical model, people are working on how to minimize the gap between the mathematical model and the numerical model. All right, without increasing the computational effort too much. So that is the idea behind that. So we are trying to get better and better approximations of reality, but at some point in time, we'll just say this is good enough for our purpose. Okay, so that is the point that I'm trying to make here. All right, so the other important point in this slide is basically not all numerical methods are created equal. So you could have two numerical methods to solve a problem, and we shall see this later on in the course. The numerical methods, each of them has certain positives, but also they will have certain negatives. So if you're trying to be more accurate, of course, that's good. But then the computational load will be higher. And in the problems we are solving in this course, the difference in computational times may not be very different between numerical method A and numerical method B that we use to solve a particular problem, right? So let's say there are 5 methods. There will be a bit of performance difference between them in terms of the time it takes to solve, right? Between a more accurate method and a less accurate method. But the time difference will not be great because the problems we are doing involves like 3 variables, 5 variables of that kind. But if you go to the industry, solving 100,000 equations in 100,000 unknowns every hour or every second hour, that's not uncommon. So there, the numerical method that you adopt will have a kind of say or impact on the performance of the method, right? So maybe uh, accuracy, robustness, and time for getting the solution. All of that will become very interesting when you're working on bigger scale problems. Unfortunately, in this course, we will work on somewhat complex problems, but they are not of the industrial scale, and therefore you may not be able to see the real difference between two numerical methods, but nevertheless we will have some illustrations of that as we go along. Now the question is, uh, in what ways can a model be useful, right? How can we make use of a model? That is the question we are trying to answer, and I alluded to this point earlier that all models are wrong and some models are useful. This is attributed to Professor George Box, who is a great chemical engineer, industrial statistician, who for many years worked at the University of Wisconsin as well, besides earlier stints in the industry in the UK and so on. He's one of the greats in the field of industrial statistics, time series analysis, and things like that. So if you get hold of this any book or any article by Professor George Box, so GEP Box, that's how you can Google his name if you want to, George Box, and he's written some very interesting books on the topic of statistics modeling broadly. Okay, so I would recommend you to take a look at that book if you have time. Now, So this statement is attributed to him. All models are wrong and some models are useful, and you will see this being mentioned by many speakers in conferences when they, give a talk on modeling, or when they write a book or something. This statement often is thrown around, and the meaning behind the statement is something that I've shared in an earlier presentation. All models are wrong in the sense that we are looking for approximations, either because we are, intentionally trying to limit the complexity of models, or we are ignorant of certain phenomena that we would even ignore some important or mildly important phenomena. So in that sense, all models are wrong. But then it doesn't mean those models are not useful, right? So you could still have good approximations, but and the approximate model could serve a very important purpose, as is happening in petroleum refineries, chemical processing units, mining industry, pulp and paper industry, biological industry, etc. Models are put to very good use in these fields, and the model keeps improving over time as we gain more and more understanding of things. So modeling is never a one-sided or a one-shot effort. It is an iterative effort. Okay, so you must understand, when somebody says all models are wrong, it is not to say that models are incorrect, etc. We know, yes, we do not know everything about the physical world, therefore no model is correct. So if somebody says I have the model of the process, that's a wrong statement. If anybody says I have a model of the process, that is okay, right? I have a good model of the process, that is also okay. But if somebody says I have the model of the process, that may be a wrong statement, because no model is exactly a replica of the physical world that we are trying to describe. So that is the real meaning of the statement. And if you model it right with the purpose in mind, then the models will be quite useful. Now, what are we trying to say in this slide is that there are three ways, or more of at least four ways in which you can make use of this model, right? The model we have. So every model has this generic structure that you see here, okay? So every model uh, uh, understands that there will be some inputs driving the model, right? So inputs is a very important characteristic of any model. Then how are the inputs transformed into outputs? So you must have a mapping that does that. Okay. So that is, we can just call it in abstract terms. We can call the model as G. So this is a function that transforms the inputs into the outputs. So if you want to look at a reactor, the input can be raw material A, right? So there are conditions within the reactor that convert A into the output B. Let's say B is the product. All right. So in this case, the input will be material A, output will be material B, and the physicochemical phenomena that convert A to B is what is called, abstract terms, it is G. So a model has three components: inputs, outputs, and then the process. We can call it as P or we can call it as G. That is just a symbol, right? So input, output, and the process, which there are three components. And depending on what you know, right, you can have different problems that you can solve with it. So in chemical engineering, right, we often do process design. In process design, what happens is the input is known, the output is known. So I will know what kind of raw materials I'll be able to get from the market. I also know what is the product I'm trying to develop to satisfy a demand that exists in society. So the input is known, the output is known, the process is a question. So how do I transform these inputs that I purchase as raw materials to products which are the output? So I have to design the system, right? I have to say, well, A must first be heated up, and then it must be purified, and then it must go through a reactor. The products have to be taken out, purified, cooled, and sent to the customer. So the design would be, what is the size of the heat exchangers? What is the size of the distillation column? What will be the size or volume or length of the reactor? So these are what are things to be designed. So in process design problems, the inputs and outputs are known, and you're trying to find out the process system. So you're trying to find out G. That's the question, right? So how do you design the various equipment? And when we say design, oftentimes it is the sequencing of equipment. and the size of each equipment, right? So that is the process design problem. Now, the second thing is sometimes, right, you may be in a situation where the inputs are known, the process system is also known, right? So G is also known, or G or P is also known, and using I and G, you can calculate the output. So the output is to be found out. So this is called a simulation problem. So when people talk about process simulation, this is what they mean. They know the configuration of the plant. They know what is connected to what and how, what is the size of each equipment, what is the, for every equipment, what are the characteristics of the inlet streams, and what is the size of that particular equipment, how many trays, for example, in a distillation column. So these things are known. So with these things, you would be able to predict, okay, this is going to be the characteristics of the overhead distillate stream. This is going to be the temperature, composition, etc. of the bottom stream that goes from a distillation column. So knowing the inputs and the system, you are asked to calculate the outputs. So that's called a process simulation problem. And definitely there will be courses in your curriculum on process simulation. Process design is very strongly emphasized in the chemical engineering curriculum. All right, so most of the courses are design courses in some sense. But towards the end of the curriculum, you will have a design project where, of course, you have to design the entire plant and then you have to simulate the response of the plant under certain conditions, right? So that is going to lead to simulation. And this is what a tool like HYSYS or HASPEN is pretty good at, right? So they are process simulation tools. The third problem is what is called the control design tools. So oftentimes what happens is the process is known, the process is fixed, the output is also known, right? The output is also known, the process is also known. And then you're asked the question, what are the inputs that will produce the outputs given the system G? So now you cannot change the system G, right? In process simulation and in control design, you cannot change the system G. That's given to us already. Somebody has designed it and put it in place. So we cannot change G. So in the control design problem, the output is specified. I know what the market wants, what I need to deliver to the market. So that's fixed. So then the control design problem is, how do I create a system that given G and the output, it will calculate I. So, this is the feedback controller. So the question there is, what is the automatic controller C, or what is going to be the operator actions, right? Let's say C is either the automatic controller or the operator who's measuring the output, who knows the characteristics of the system, that means knows something about G, and then fiddles around some valves and so on, so that delivers the right input so that the system will produce the output as desired. So this is the control design problem. So you will have a course called process dynamics and control in your curriculum. That is basically this. The system is known and given, the outputs are specified, and then you have to find out a way on how do you calculate the right inputs so that you can deliver what the market wants given the system that you are provided with, right? And interestingly, the system will be hit by disturbances continuously. All right. So, for example, if you take a look at something like COVID-19, the desired output. That means you want zero infections, right? Or as minimal infection as possible, minimal deaths as possible, right? Minimal hospitalizations as possible. So those outputs are specified. We know the nature of the disease, how it spreads, right? We know something about it, right? So the government, right, for example, or the health ministry tries to find out the input actions. What should be the quarantine measures? What should be the safe distancing measures? What should be the vaccination measures, etc. So if you're running an organization, of course, you can always change the design of the organization. You can always influence what the market wants sometimes, but the lever in your hands is the input variables. Those are the policy decisions that you take. So if you're managing an organization, the control problem is more like a policy development problem. Okay, so that is what it is. The fourth category of problems that we will touch upon is what is called process optimization, right? So that is slightly different from the other three. So in a typical process, you will have levers that you can manipulate, right? So the levers can either be a design variable or it could be an input variable that you can control, things like that, right? So it is kind of a mix of a few things. But we will discuss this problem in some detail later. So process optimization problem again is how do we make use of the levers that are available in the system so that you operate it for maximum safety or maximum profit or least effect on the environment and things like that, right? So that is another category of problems that are extremely useful. This optimization is a very, very useful technology. In fact, that is what goes on, as a common thread between all of these problems. Because whenever we design something, we will try to optimize. There will always be trade-offs of certain kinds, etc. Right? So optimization is a pretty useful technology. So if you come across any course in your curriculum in your university or an online course or a lecture that talks about process optimization, please take it. All right, I will stop this video segment here and I will catch up with the rest of the things in subsequent videos. Thank you for your time.